This lesson is about sets and tuples. So first, let's just start with the definition of a set. A set is just an unordered collection of objects. So the following definitions could all be considered sets. So you see here I have these kind of curly braces, and I say the numbers 1, 2, 3. So that's a set of the numbers 1, 2, and 3. I also could just say all multiples of 7, and that could be a set of numbers. That is an infinite set of numbers, but it's still a set of numbers. I also could have a set of different types. So I could have apples, the number 7, and a Boolean true. And that's fine. Another thing important to make sure you understand about sets is they do not inherently have an order. So just because in this last example, apples is the first element listed in our set, that doesn't really mean like it has an index necessarily or anything like that. So it doesn't necessarily mean it's actually the first element. That's just how it was typed out. And so I'll talk a little bit more about what I mean by not having an order further on. First, I want to talk about the size of a set. So a set is a finite set if it has a finite number of elements. And conversely, if it is not finite, then it's an infinite set. So if A is a finite set, then the number of elements in A is called the cardinality of A. And you'll often see it denoted with this these two bars on either side of the name of the set. So for set A, the two bars on either side is talking about the size of set A, the number of elements in that set. So an example for the set that I defined previously, 1, 2, and 3, since there are 3 elements in that set, its cardinality is 3. So another set I talked about was all multiples of 7. And as I said, that could be infinitely many numbers. So it's technically an infinite set. And cardinality is more complicated when you're talking about infinite sets. And that's something we will get to farther on in the course. But for now, we're just focusing on the cardinality of finite sets. So don't worry about the cardinality of something like all multiples of 7 just now. Another type of notation you might see is this, sometimes it's called is an element of, or just an in notation, and it just kind of looks like a curly brace with a line through the middle. And basically it just means that something is an element of a set. So if little a is in A, this means A is an element of A. And similarly, if I wanted to say something's not in A, I could say this little a is not an element of A. So for some examples, if my set was apples, bananas, and oranges, then apples is in A, right? Because apples is an element of A. But blueberries is not an element of A because blueberries is not one of the things listed in my set A. Some other notation. And I talked about this briefly in the pseudocode lesson about how hard brackets are basically inclusive of all of the numbers between A and B. So it's from the numbers from A to B, including A and B. But if you have the parentheses, then you're just including the numbers between A and B, but not A and B themselves. So an example is if we're doing with the hard braces 1 to 5, then we're including 1 and 5 and then every number in between. But if we're doing with the parentheses 1 to 5, it's just going to be 2, 3, 4. So it's the numbers between 1 and 5, but not the numbers themselves. You can also kind of combine these. So you could maybe do a hard brace on one side and then a parenthesis on the other side. And so if you did that, that means we'd be including 1, but not including 5. So it'd be 1, 2, 3, 4. Now, a certain type of notation you'll see, especially if you're talking about larger size sets where you don't want to write out every number, you might want to use set notation to describe your set. And that's often done using these curly braces. And so the idea is that You on the left side of this bar, you're going to have some type of function that describes all of the elements in your set. And this will be what you'll be on the right side. You'll be talking about what you'll be using in that function. So let me give you a little example of that to show you what I mean. So if I'm talking about the set 1/2, 1/4, 1/8, notice that these all are 1 over something. So I could describe my set by saying it's 1/n, where n is 2, 4, and 8, right? Because it's 1/2, 1/4, 1/8. So I could describe my set, and it's kind of interesting because I'm using another set inside this definition. That's very common on this right side. You might see another type of set we're talking about, but maybe something a little simpler, like here we have 2, 4, and 8. So this would be one way I could define this set. And we'll get more practice with this in the future. Another type of notation that's going to be really common that you'll see is the subset notation. And so basically A is a subset of B if and only if every element of A is an element of B. So B has to basically contain everything that is in A. And this is often written with this type of notation. So this is actually subset equals. So this includes the case where A could also be equivalent to B. If A is a strict subset of B, then you also could use the notation just this subset symbol, just this subset symbol without this line underneath. So this line underneath means there's the possibility that they also could be equal. So it's still technically correct because it's like a less than or equal than symbol, right? So A is a subset or equal to B, or you could just say A is strictly the subset of B. And either is technically correct. So in this case, it could be either one. So we could say A is a subset or equal to B, or A set A is just the strict subset, is what they'll sometimes call that, of B. And so one way we can think about whether or not two sets are equal we can use this definition of a subset. Because if two sets are equal, then they're going to be each other's subset, right? So the other thing I want to emphasize here is this is an example of two equal sets, even though A and B aren't, the elements aren't in the same order, but that's okay because remember, I said ordering doesn't matter for a set. So even though A is 1, 2, 3 and B is 3, 2, 1, since they have the same elements, they are considered equivalent. And then going back to what I was saying about subsets, every element of A is in B, and every element of B is in A. So A is technically B's subset, and B is technically a subset of A, so therefore A equals B. So this is kind of an interesting property of how we can express equality using this kind of subset notation. And this could be useful because sometimes if we want to prove two sets are equal, sometimes it's easier to prove these kind of properties than just directly showing they're equal. Another type of set operation we're going to learn about, and we'll learn more about this in our next lesson as well, but the first one we're going to learn is called intersection. And so this is the set of elements that are in both A and B. So I think the best way to show this is with just an example. So if A is apples and bananas and B is bananas and oranges, the intersection of A and B is just bananas. So it's elements that are in both A and in B. And you can kind of think about how that ties into your logic, right? So X is in the intersection of A and B. That really just means X is in A, and then you can pretty much just do a logical and X is in B. So that's why it isn't really like, it's not a coincidence that this intersection symbol kind of looks like your logical and, because they're doing something very similar. And so since we have something for the and operator, we also have something similar for the or operator. So A union B is a set of elements that are in either A or B. So it has to just be in one of those two sets. So again, for our same example, apples, bananas being A, and B being bananas, oranges, the union is apples, bananas, and oranges. So it's the elements that are in either A or B. And again, we can kind of tie that back to our logical OR operator, right? Because X is in A union B, if and only if X is in A or X is in B. So again, you have this kind of logical OR that looks pretty similar to this union symbol. There are lots of different sets in this universe, but there are a few that we're going to be talking about a lot in this course, and there's some that you've already probably heard of. So some symbols that will represent these sets I'll introduce to you as well. So the set of natural numbers will be denoted by this N symbol here, and so that's something to get familiar with. And it's just the set of all whole numbers greater than or equal to 0. Now, so this is just basically 0, 1, 2, 3, 4, all the way to infinity. The reason I did put an asterisk here is that in some circles, a lot of mathematicians disagree on whether or not 0 should be included in the natural numbers. So if you happen to forget 0 in your natural numbers and start them at 1, I'll allow it. The reason I chose to include 0 is because in computer science, we tend to start our indexing at 0, so it makes more sense for us to include 0 in our set of natural numbers. But again, if you wanted to start at 1, that's fine. It's just basically non-negative numbers, whole numbers, and they just go to infinity. Similarly, you have your set of integers. So it's like your natural numbers, but it includes negative numbers as well. So you have your positive or non-negative numbers all the way to infinity, but then you have your negative numbers, again, whole numbers all the way to negative infinity. And this is denoted using this Z symbol. And so again, these are just symbols that you might want to get used to seeing because these are very common. So this N to denote the natural numbers, this Z to denote the integers. Another set of numbers you will see, and we'll talk more about these in the future, but this is the rational numbers. And this is the first set that I'm really showing you that's defined using that set notation. The rational numbers are just basically any numbers that can be represented as a fraction. So rational numbers are your fractions. So this is my set notation where I have kind of my formula on one side, and then I have like what goes in the formula. So it's P over Q, where P and Q are both integers. So let me just let's think about this a little bit. So you have P over Q, and both of these are integers. So you could have 1 over 2, -1 over -2, which is actually equivalent, but that's fine. You could also have, 3 over -4. Anything that's an integer over another integer would be in this set, right? So on our left, we have kind of like the formula that describes it, and then the elements that are going in that set. So that's our rational numbers. And so look for that Q to denote the set of rational numbers. Another set we'll be talking about frequently is the set of real numbers, R. And so this is numbers that are technically they could not be necessarily represented by fractions. So a really common one would be pi, right? So pi is very famously, this kind of really long number, 3.14159, and so on. And so that's technically a real number, but it's not a rational number because pi can't really be described as a fraction. And it's not an integer or a natural number because it's not a whole number. So the set of real numbers kind of covers these other numbers, basically. It covers, so technically like an integer, 3 is still a real number. It's also a natural number and an integer. and technically a rational number, but it also is a real number. So you can kind of think of your real numbers to be like this big set right here. And then, so this is R. And then you have your rational numbers, Q. And often in math, we kind of just write it like a Q like that. And then you have your integers, Z. And then inside your integers, you have N, your natural numbers. So that's how you can kind of think of like the hierarchy, is that the natural numbers are actually inside the integers are inside the rational numbers, and then the rational numbers are inside the real numbers. And so the numbers we're not really talking about here are the imaginary numbers. And so we could just kind of think about them over here, your imaginary numbers. And those are like the ones with I in them. So that's if you know you have your like the I, which is equal to the square root of -1. Those are your imaginary numbers. And so that's basically what we're not including when we're talking about real numbers. So sometimes we can make different types of sets. So we can kind of talk about sets in a different way or define them in a more specific way. So they have more specific properties about them. And so a tuple is a type of set, but it's one that we talk about more specifically. And so what it is it's usually called a k-tuple, where k is the number of elements. So it's like the length of the tuple. And it's an ordered sequence of k elements. So it's like a set, but this time we do have ordering. So like there's always something, this is where you can kind of think of things actually being indexed. But it is a fixed size. So this is a data type you learn in your intro to programming class, and this is also something we sometimes will reason about here when you're trying to represent things mathematically. Tuples really can come in handy. And so the most common tuple seen in math is the coordinate pair x, y on a graph, right? It's always of length 2, and you always have x first and y second. Another word for a tuple is an ordered pair. So that might be something that you've also heard that called. And they are equal if and only if all of the corresponding elements are equal. So this is one way we can kind of express that now using our set notation, right? So what am I saying here? Basically, if I have one tuple, A1, A2, A3, and then I have this tuple B1, B2, B3, it must be the case that A1 equals B1, A2 equals B2, and I'm actually gonna just go ahead and use my AND operator, combine these, and A3 equals B3. So for the coordinate pair, right, 1, 2, let's say if it's a 2 tuple, we have a 1, 2, that would be only equal to the other tuple 1, 2, right? But if we had the tuple 2, 1, that's not equal, right? And so this is how we're saying that mathematically. So A1, A2, all of this tuple would be equal to a similar B tuple if for all I in its indexes. So now we're talking about I is basically talking about the indexes here of our tuples. So we have I could be 1, I could be 2, all the way to k. So for all of those i's, A sub I should equal B sub I. This is actually missing, so it should say A sub 1 should equal B sub 1, B sub 2, B sub k. So this should go right there. So basically these two are equal if for all of these indexes, these elements are matching. Okay. So a common operator you'll see with tuples is this idea of a Cartesian product. So I'm trying to move this. It's going off the page at me. There we go. So this idea of this Cartesian product is you're finding basically like all combinations between two different sets. So this is and usually this creates tuples because it's ordered. The Cartesian product takes two sets and it creates tuples. Or it could take multiple sets if you're taking the Cartesian product of multiple sets. But generally, you take a Cartesian product of two sets, and then it creates this kind of like two tuple or ordered pair. And so this is how you could define it using your set notation. You have A times B, and so this times right here denotes what a Cartesian product. And then it's basically an element of A and an element of B. So for each element in A and for each element in B. And so again, you see my set notation here, right? So it's an ordered pair AB, where A is an element of A and B is an element of B. And so here I did it where I did L and D as my two sets, and A, B, C are the elements of L, and 0 and 1 are the elements of D. So if I take the Cartesian product of L and D, the first element should be an element from L, the second element should be an element from D, and it should be all combinations of those elements. And similarly, if I did D times L, then you'll notice that my first element is actually from D, and then my second element's from L. So it does change the ordering, right? So now I have 0A, 0B, but again, it's all combinations still of elements from D and from L. And you can also take the Cartesian product of something like twice. So you can take a Cartesian product of a set with itself. So you can do L times L, and that could also be written as L squared, you'll sometimes see. And so that's AA, AB, AC, BA, and so on. So it's all combinations of elements from L, but it's all going to be tuples of 2. And so this is actually kind of something we'll talk about a little more, because you'll see this sometimes to represent like one common representation is back to these like coordinates. So if you had like an XY coordinate, like you had XY like that, what you might see it as is XY is going to be in R squared, because the basically it's a set of numbers where the first element is in R, so it could be 1.0, and then the second element is in R, this is our real numbers, which could be 2.0, and it's all possible combinations of real numbers, right? So this is often this like times or this square notation is often used to kind of talk about relations like that. And we'll talk more about those kind of things in the future, but I just want you to get used to that type of notation because that's something we'll be seeing more. So 2 other things to note about the Cartesian product. It is associative, so you can always rewrite it. So you can like move the parentheses, and it still means the same thing. And similarly, one thing you should know though is it is not commutative. So, and that's what we showed right here, right? So L times D is not the same thing as D times L because it changes the ordering of the result. So that's just something to also make sure that we're clear on, that is the Cartesian product is not commutative. So now we'll talk about sequences, strings, and series. So these are all other types of sets. They just have different names because they have different types of behavior. So a common one that you might have seen in your intro to coding class is a list, right? So that's a tuple. A list is very similar to a tuple, right? Because it's ordered. So, lists could just be like the numbers 1, 2, 1, 2, 3, could be a list, something like that. But the idea of a list is you can add elements to it, right? So I could add 4 to it. So it's not a fixed length like a tuple is. You can kind of change the length. And so that's the idea of a list. And so that's a very common one. And similar to tuples, though, they still have this ordering, right? So you still have your 0 index, you still have your 1 index. So you have this kind of indexing on these elements where there's like a first element, a second element, and so on. And remember, in computer science, we do start our indexing at 0. So the first element is the 0th element. Second element is the first element. Third element is really the 2 element at index 2. So I know that can be a little off-putting, but just remember that you're starting your indexing at 0. So another thing you might see is a sequence. So that's a list that could be infinite. And so we'll talk more about that, like how you define a sequence, but it's very similar to a list, but it could actually be infinite. So it's not something like confined that we're necessarily defining like the way I just defined a list. Another thing you might see is a vector. So this is something you might have seen in previous math classes. And so those are, the ones that are often notated with these kind of arrows in between on either side. And usually that just means they have other types of features like direction and things like that. Other things you also might see are matrices, arrays, or tables. So all of these are types of sets. They just have different rules to them and different types of representation. And so the things that we're going to learn for talking about sets and thinking about sets, you can end up applying to these other data structures in the future. One operation that I want to make sure you're familiar with is concatenation. And so that just joins two strings or lists by putting all elements of the first string or list behind the second, right behind all the elements of the first. So I think the best way to show is just by example. So if you're concatenating hello and world, you get hello world. And so that's just an operation that we should be familiar with, is the idea of concatenating. So now to go a little more into what we were talking about with series. A series is a sum of a sequence of numbers, and you're replacing your commas with plus signs. So instead of just having like a sequence like x1, x2, x to the n, you could represent it as a series. So you could represent it as x1, x2, the sum of x1 and x2 all the way to x sub n. And you often write this with the summation notation. And in this class, I think sometimes people do get thrown off by the summation notation. And so this is something just to make sure you get comfortable with, is this idea that like this x1, this expression can just be written as a sum. And here you'll see it like where the I is kind of here, but you might also see it like down here, I in 1 to n of x sub I. And so this is talking about this sequence. And so kind of being able to like understand this representation between these two is important. So other things we're going to want to do, and this is going to be a big part of this class too, is learning how to count elements in sets. And so this is just saying like, okay, I'm looking at maybe different types of sets, or I want to rearrange certain things in my one set, different options, but I basically want to be able to reason about it that way and say, okay, like how many items am I working with now? And so there's two big rules that we're going to use, and the first is called the sum rule. And so both of these rules, if it doesn't make perfect sense in English, that's fine, because we'll give an example and then I think it'll make a lot more sense. But the sum rule states that suppose that each element of a set has an assigned type, then the total number of elements is the sum of the numbers of elements of each type. And you'll see an example of this in your assignment as well. But basically it means I can break up the elements of my group into different types and then sum the numbers in each of those types together, and that is the number of elements in my set. And similarly, we have a product rule. So you could talk about elements of a set that have features that can be chosen independently. So this is what I was kind of talking about, rearranging elements of your set. And the number of elements is the product of your numbers of choices. So we'll talk about both of those two things with an example. So first we're going to talk about this sum rule. So I have a set of 6 different math books, 5 different philosophy books, and 3 different religion books. How many books do I have? And the answer is by the sum rule, we just add them up. So we say the number of math books, which is 6, the number of philosophy books, which is 5, and the number of religion books, which is 3. So that would give me 14. So I just have a set of books, and this is basically the size of my set of books. And instead of just counting each book individually, I kind of counted them by their subsets based on their type, and then summed that together. And that's basically all that the sum rule is saying. Now, the product rule is a little more complicated. So this is saying I want a set of 3 books, and I want one of each type. So I want a math book, a philosophy book, and a religion book, let's say. And so I want all tuples basically of the form little m, little p, little r, where m is a math book, p is a philosophy book, and r is a religion book. And I basically want, all different combinations of the set of math books I have, the set of philosophy books I have, the set of religion books I have. I want to consider all possible combinations of those. And so the product rule tells me I can just multiply it by the number of each type that I have. So since I have 6 math books, I have 5 philosophy books, and I have 3 religion books, my answer is just going to be 6 times 5 times 3, which is 90. So there's 90 different ways I could combine my 6 math books, 5 philosophy books, and 3 religion books. And so another way we can kind of think about that is using the Cartesian product. So you could think about it as I'm going to take the Cartesian product of the math books and the philosophy books and the religion books, and that's going to give me all of these tuples. And so basically what I'm saying is, okay, what is the size of the Cartesian product? That's basically what I'm computing here. And so what's kind of cool is we did this, right? We did the size of math books times the size of the philosophy books times the size of the religion books. But it's giving me also the size of the Cartesian product of those things, because it's computing all of these possible tuples, which is what I just counted right here. So basically I can compute the size of the Cartesian product just by taking the product of the sizes of each of the sets. And that's basically what the product rule is saying, is that I can kind of break this up by type and take the individual products and get the Cartesian products to kind of reason about all the different combinations I can make. Another type of operation we're going to learn about on tuples specifically is this idea of permutations. So remember, tuples are a type of set, but they are ordered. So I have A as the set, but if I wanted to rewrite it as tuples, and so really this should be parentheses here and here. So all these elements should really have parentheses around them. But basically the idea is it's the all kind of orderings of the elements without any repetition. So Alice is not going to show up twice in my all my permutations of A. Alice is not going to show up twice. But in this case, the order does matter, right? So even though Bob, Alice, Chris, and Bob, Chris, Alice have the same elements, they're in a different order, so they're considered different. And so this is the idea of the permutations, is I'm basically considering all different orderings of my elements of my set. There is a way to compute the number of permutations of n items, and it's with this n factorial. And so n factorial is probably something you've seen before. And it's just the product of n with n minus 1 times n minus 2 times all the way down to 1. So every number less than n. And so some ways we might, for this example, for A, well, we have 3 elements, right? So the number of possible permutations is 3 factorial. And 3 factorial is just 3 times 2 times 1, which is 6, right? And so just to get more comfortable with this factorial, right? Like 5 factorial would be 5 times 4 times 3 times 2 times 1, right? So anything factorial is just itself times all the numbers less than it going down to 1. And so again, for A, we have a set of size 3. And so we're creating all possible 3 tuples, right? All possible permutations of length 3 of this set of elements. And so that will be 3 factorial many possible combinations. And so this makes sense, right? Because if we go back to our previous slide, that was the case, right? We had 6 different permutations that we created. So this is just a way of computing how many of possible permutations we're going to be making. And so we can kind of use this idea of permutations on a more complicated example. So let's go back to our example with the books. We have 6 math books, 5 philosophy books, and 3 religion books. And we want to know a way to arrange 3 of the 14 books on the shelf and get one of each type. All right, so let's get a better visual of what this problem is. So we might want to do like a math book, a philosophy book, and a religion book. Or we might want to do a religion book, a philosophy book, and a math book, right? And so we might want to do all different orderings of a book. But also remember that this math book could be one of 6 different math books. And this philosophy book could be one of 5 different philosophy books. So there's a lot of different possibilities here in the ways we can choose the book and choose the ordering. And we have to kind of combine those 2 things. So let's break this down into a smaller problem, because the things we've learned so far, actually, we can learn how to do this. So this is just me reiterating it. So let's just say I just want 3 books, one of each type from the shelf. And how many possible combinations are there? Well, we already did that problem, right? So if I just wanted, so this is just if I wanted one type of math book, one type of philosophy book, one type of religion book, how many possible combinations if I just wanted those 3 books? Well, our product rule told us that was just 6 times 5 times 3. And so this was telling me, like, again, this was me kind of choosing, you know, I was talking about how I had like this, like a math, philosophy, math, philosophy, religion, and this was like which this could be 6, this could be 5, and this could be 3, right? And so this was just telling me that. But now our problem's not done, because I want to think about the different orderings though. So I am choosing these books, but I also want to consider if I want to do religion, math, philosophy, for example, or all the other different permutations of my books. So this is like, I'm thinking about, you know, the aesthetic of my bookshelf, how I want to order these books. So if I just wanted to see how many times I could arrange a set of 3 books, regardless of type, this is just the same as counting how many permutations there are, right? So if I just wanted to see the way I could order these 3 different types of books, I would just do 3 factorial, right? This would be my ordering of my 3 tuple, right? Which is basically what I was just talking about. This was this like MPR, RPM, all of these combinations. That's what I want to see how many possible of those permutations are. So that's what that is. So that's 3 factorial. And now I can combine these 2 answers. So 3 factorial is the amount of different ways I can order it. So if I just do this, like ways I can order them is 3 factorial. And this is the types I can pick, we'll call it, which was our 6 times 5 times 3, right? So this was my product rule, and this was my permutations. And so I can just multiply these together to get the total number of ways I can pick a different type and order it, right? So I'm just combining these two now, these two options. So now I want to kind of continue with more examples of permutations. So I want to talk about other ways we can kind of play around with these notations or with these operators. There's one kind of interesting feature specifically about the factorial that we need to kind of learn and learn how to work with a little better. So let's say how we, now we're going to look at all, we have 14 books. Let's say we want to look at how many different ways I can arrange my books. So that's pretty straightforward. I have 14 possible permutations of my books. So this is just on my bookshelf. How many different ways can I, display my books of my 14? That would be 14 factorial, right? So that would be my 14 times 13 times ... so on. So that would be just how many times I wanted to, if I wanted to put all 14 books, that's how many possible ways I could order them. But say I just wanted to see how many, I just wanted to pick 3 of those books, not worried about type. I just want to pick 3 of those books out of my 14. And so I want to see how many of ways I can order those 3 books. So I have to kind of stop my factorial early because my first choice, I'm choosing from 14 possible books, right? And so that'll be 14, and then I multiply it by 13 because now I'm choosing from, I've taken one book out and I put it on my shelf. So now I'm choosing from 13 possible books. And I take this book out and put it on my shelf. So now I'm choosing from 12 possible books. And so I just multiply these together to get how many ways I can order any 3 of those 14 books. And so this type of notation has a different way of being expressed, and that's what I kind of want to talk about. So basically, the way you can express this 14 times 13 times 12, you can also express it this way: 14 factorial over 14 minus 3 factorial. And so I kind of want to talk more about why this works. And so the idea is that you're basically just subtracting the number of how many terms you want to include in this factorial. And so I think a smaller number might be a better example. So say I have 5 factorial. So 5 times 4 times 3 times 2 times 1. And say I just wanted to do 5 times 4. So that means I just want 2 terms, right? So the way that this formula works, I would write that as 5 factorial over 5 minus 2 factorial, right? Because I just want these first 2 terms. And so if I break this down, right, I can kind of separate this out using how my factorial works. So 5 factorial is 5 times 4 times 3 times 2 times 1. And 5 minus 2 is 3. So 3 factorial is 3 times 2 times 1. And you'll see now the way, fractions work, I can cancel out numerator and denominator. So I can cancel this 3 out, cancel this 2 out, cancel these 1s. And now I just have my 5 times 4, which is exactly what I was looking for. So that's kind of the reasoning behind why this works. It basically kind of cuts the tail off of your factorial. And so that's why we use this formulation. And you're like, okay, but this is easier to write than to have to think about this. Why am I doing that? But sometimes for bigger problems and things like that, you're gonna need to use this notation. It'll be a lot easier to represent things this way sometimes. So you'll want to know this type of formulation. And I know counting can be stressful sometimes and overwhelming, I think it's just good to remember your core examples and go back to them and just keep practicing. I really think that's the best way to do it, and to kind of remember like which rule you might be using. And I think the assignment does a pretty good job of helping you kind of get more practice with that as well. And so again, this is just the generalized version of what I just said. So if you want to take n factorial, so here our n is 14, and you want to stop after k terms, so 14, we want to stop after 3 terms, we just do n factorial over n minus k factorial. So this would be 14 factorial over 14 minus 3 factorial, or the example I drew out, 5 factorial over 5 minus 2 factorial. So this is just a generalized way so you can kind of remember that rule. And this is actually called a K permutation because you're taking it from a bigger set, but you're taking permutations only of size K, right? Like this was permutations of size 3 from our set of size 14. So that's why it's called a K permutation. So similar to a permutation is a combination. And so this is a set of, with k elements chosen from a set of n possible items with no repeats. But so it's very similar to a permutation, but since these are sets, order doesn't matter. So this is like if you are a chaotic book owner and you care what books are on your shelf, but not what order they are on your shelf, this is for you. So you care about what elements there are specifically, but not the order in which they appear. So you want to compute all 2 combinations of A, B, and C. So this is all different ways you can combine 2 elements from this set. So you could have AB, AC, or BC. But if I wanted to do permutations, like taking it back to our previous example with permutations, we care more about ordering. So AB and BA are 2 different things. So I'd have to consider AB and BA and AC and CA, where in this case, I wouldn't have to do that because order doesn't matter. So AC and CA would be the same set. So only have to list it once. So in this case, there's 3 possible 2 combinations, but there's 6 possible 2 permutations. So it's good to just kind of understand the difference between combinations and permutations. For combinations, you can just think like, order doesn't matter. Always the best thing to remember that. And so this is often calculated using this idea of choose. This is this operator, it's called choose. And so you write it as n choose k. And so you might also see it written this way, like C of nk or nck or comb nk because it's combinations. So in our last example, we had a set of we had the set ABC, and we were choosing the number of 2 tuples, right? So 2 elements. So A, B. Sorry, not tuples sets. So AB, BC, and so on. So this would be the size of the set. So that's going to be 3. And then your K is going to be 2. So it's going to be 3 choose 2. Because you're taking it from a set of size 3 and you're considering all combinations of length 2 or of size 2. And so, again, you'll see this often denoted as with these parentheses, so you have 3 choose 2. So the way to actually compute the value of 3 choose 2 or n choose k is by this equation down here. So you have n factorial over k factorial times n minus k factorial. So for 3 choose 2, you'd have 3 factorial over 2 factorial times 3 minus 2 factorial. That's equal to 3 factorial over 2 factorial times 1 factorial. And then you could simplify this out. So 2 factorial, or we could just write it all out just for practice. So 3 times 2 times 1 is our numerator. And then 2 times 1 is 2 factorial times 1 factorial, which is just 1. So 3 times 2 times 1 is 6. And 2 times 1 times 1 is 2. So 6 divided by 2 is 3. So there should be 3 possible combinations. And in our example, that was the case, right? Because we had A, B, B, C, and then AC, right? Those were our 3 possible combinations. So that ended up being, so that's how this equation works. So I'm actually going to end the lesson here. I did include a couple slides just kind of explaining the reasoning behind how this formula works, like why it's developed, why this works every time. And so if you wanted to, you can continue on the next couple slides and go through that example to just kind of give some meaning behind it. But I think it's also fine to just stop here if you just want to focus on like remembering your rules for counting.